Hello, welcome to this lecture about pressure in ducts. Pressure changes in air ducts and water ducts is the reason why pumps and fans must be used, which contributes to energy use. So a good design is necessary. Pressure distribution is also important for the right distribution of air and water to the right place. You may remember from another lecture that the electrical power P needed to power ventilators in the mechanical ventilation systems is the volume flow rate of air in cubic meter per second times the pressure loss in the system, the whole divided by the efficiency of the ventilator and its motor, eta, being generally around 0.6. Exactly the same formula can be used for water pumps. As there are many pumps and ventilators in an HVAC system, they may use a substantial energy and therefore limiting the pressure losses is important. But how to calculate this pressure loss? Realize first that pressure can be seen as energy per unit of volume. You see it in the equation. V times delta P is in watt, which is the same as joule per second. As V, the volume flow rate, is in cubic meter per second, delta P has the unit of joule per cubic meter, so pressure is volumetric energy. The unit of pressure is Pascal. 1 Pascal is a force of 1 Newton exerted on 1 square meter surface, so pressure can also be seen as a force exerted on a surface. This is a very useful definition to understand pressure. In SI units, it is expressed in kilogram per meter per square second. What is pressure? Well, if you put a fluid in such a U-shaped vase, the water has exactly the same height in both branches of the vase. This is because the atmospheric air pressure, which is the pressure exerted by air on the surface of the water, is the same above the two branches. The water is not moving, there is no flow. We call the pressure in the water the static pressure because it is not moving. But what happens now if I try to push the water by exerting a force in its surface in one of the branches like that, using a piston-like shape? I push hard, so the pressure is high. For sure, the water will start moving, creating a flow rate, and the water will flow out of the vase. So, pressure and flow rate are linked together, and by adding pressure at one side, I have overcome the atmospheric pressure and brought the water in movement. Let's consider first the case where there is no moving fluid, just an open container with a fluid in it. There is a pressure exerted by the atmosphere on the surface of water, PE. But what is the pressure lower in the fluid? In Z1 and in Z2. If you have diving as hobby, you know that the deeper you go, the higher is the pressure. And that is because the deeper you go, the higher the water column above you. So the larger the force the whole water column exerts on you. So the total pressure you feel in Z2 is the sum of the atmospheric one, PE, and the one of the water column, rho times G times Z. This term, rho G Z, is nothing else than volumetric potential energy. Note that in a pressurized or depressurized environment, P is not the atmospheric pressure anymore, but the pressure of the environment. If we put this water vessel into a bigger vessel full with compressed gas at 2 bar, PE will be 2 bar instead of 1 bar. Let's look now at what happens when the fluid is moving. We have seen that adding pressure will produce a flow rate. We also have seen that pressure is energy per cubic meter, so we can make an inventory of the different kinds of energy coming into the volume under consideration, our two-branched vase with its water from previous slide, for instance. First, there is the static pressure, which is the pressure when the fluid is not moving, consisting of PE and the potential energy. Then, if the fluid is moving, it has kinetic energy. Kinetic energy is half times mass times the square of the velocity. If we want to express it in terms of pressure, we just need to divide by the volume and we get this term with rho, as m is rho times v. And that's it. If we assume that the fluid remains at a constant temperature, so there is no heat removed or added, which is a good approximation of what happens in insulated ducts and pipes. So we end up with this formula for the total pressure of a fluid in Pascal, which is the same as the energy contained by 1 cubic meter of this fluid. It is the sum of the static pressure and the dynamic pressure. Pressure is volumetric energy, so just like energy, it is conserved. This is known as Bernoulli's principle. So in a pipe, the total pressure at point 1 must be equal to the total pressure at point 2, whatever happens in between. However, we overlooked something, and that is the friction energy coming free in the volume. Any flow will cause friction along the walls of the pipe, resulting in a slowing down of the flow and a bit of heat being created in the pipe. So the real equation is this one, and the one above is this one and not the one above. Friction is something that happens over the length of the pipe. That's why at the starting point in 1 we don't have such a term. It builds up, let's say. It is also valid whatever the slope of the pipe. What does that mean for our air and water ducts? Pressure is volumetric energy, so just like with energy, we can make a balance. Let's start with a very important case where we want to maintain a constant velocity in the pipe. That is what we normally want to do, and start from the original equation where V2 is now equal to V1. The environmental pressure has not changed between 1 and 2, so we can eliminate it. And in our case, Z1 equals Z2. So we end up with half rho times V1 square equals half rho times V1 square plus the friction pressure. There is clearly an unbalance here, meaning that the state of having the same velocity in the 2 points is impossible. The pressure is not conserved. So, either the velocity at point 2 will decrease below V1 to compensate for PL, or we need to add pressure at point 1. And that is what a pump or a fan does. It adds the needed pressure to compensate for friction losses arising further in the pipe. What happens now if there are changes in the section of pipes? The environmental pressure has not changed, but the height of the fluid column has. In my example, if we look at the center of the flow, it is half the original one. So the static pressure, rho g Z1, decreases. Because Z1 is larger than Z2, half rho V1 square must be lower than half rho V2 square plus the friction pressure. In general, the friction pressure is much smaller than the dynamic pressure, so in general the velocity V2 will be higher than V1. We can visualize that like this. The total pressure remains constant, and the decrease in static pressure leads to an increase in dynamic pressure. In the end, it comes to what was described in earlier lectures. At constant volume flow rate, the smaller the section of the pipe, the higher the velocity. Static and dynamic pressures can be measured by using sensors called pitot tubes. The capillary tube measuring the static pressure has no opening towards the flow and is therefore not sensitive to it. The right tube measures the total pressure. As you see, it remains constant all time, so the difference between both is the dynamic pressure term that allows to measure the velocity of the flow if the friction pressure is not too high. You see in the picture that the static pressure decreases after each smaller section, while the dynamic pressure increases. There are nowadays many other ways to measure pressure and velocity. We just described it extensively. When a fluid flows in a duct, friction pressure is unavoidable. It is good usage to call this friction pressure pressure loss, as we have to compensate for it with a pump or a fan to ensure a constant fluid velocity and a constant volume flow rate. They are generally referred to as delta P. In this slide, we look first at the pressure loss arising from friction in a straight pipe and call them PFL. This pressure loss has been empirically determined to be the friction coefficient lambda times the length of the pipe divided by its inner diameter times the dynamic pressure ρ times V square divided by 2. Note that in many handbooks the friction coefficient lambda is referred to as 4F. The friction coefficient lambda is a function of the Reynolds number. In fluid mechanics, the Reynolds number is a very important dimensionless number predicting the flow pattern. It depends on the viscosity of the fluid, its velocity, and the diameter of the pipe considered. Nu is the kinematic viscosity and mu the dynamic one. If the pipe is not circular, the parameter d must be changed to another one, characteristic for the pipe under consideration. Anyhow, at low Reynolds number, the flow is laminar, while at high numbers it is turbulent. When a flow is laminar, which is when the Reynolds number is smaller or equal to 2300, the friction coefficient equals 64 divided by the Reynolds number. When Reynolds is higher than 3500, the flow is fully turbulent, and the friction coefficient depends then also on the smoothness of the pipe, epsilon. The rougher the pipe, the higher the friction coefficient. In the frame on the right, you see some values of epsilon for diverse materials. The actual value depends a lot on the manufacturer. If the Reynolds number is in between, an interpolation can be used as given in the last formula. There are also other formulas being used, like the one from Nikuradze or the Blasius equation. In the end, it does not give very different results. Finally, if you don't like these calculations, you can use a diagram like the one of Colebrook and Moody, who calculated it for you. You see on the left the line for laminar flow. It does not relate to the smoothness of the pipe. The other lines are for turbulent flow and depend on the smoothness. Finally, there is friction arising from bends, branches and devices like fittings and valves, but also all devices like heat exchangers. They all have to be taken into account. Generally, producers of valves and other devices provide the pressure loss. As for bends and branches, there are many tables and graphics that can be used to calculate them. You see on the left two examples. Above is for the T branch of a duct. The Xi coefficient can be found on the y-axis, while the x-axis represents the ratio of the velocity in a branch, 2 or 3 in our case, and the velocity in the initial pipe, 1. Depending on this velocity ratio, Xi can be determined. For a bend, we should look at the diagram below. This time, the x-axis represents the ratio of the radius of the bend with the inner diameter of the pipe. Those are only examples. There are many tables showing these coefficients for diverse configurations and branches. In the end, the total pressure loss that must be compensated by a pump or a fan is the sum of all friction losses in all straight ducts served by the pump, plus the sum of all friction losses arising through bends, branches and devices. So once you have described the specific pipe network of a building, you need to make these calculations. There are many software tools that can help you doing that. In this lecture, you learned about pressure issues in ducts and pipes. You now know what is the difference between static and dynamic pressure, and above all, you have realized that flow and pressure always goes hand in hand. You are aware that to compensate for friction pressure, we need to add pump or fan energy to the system if we want to keep the velocity of the fluid constant. This is because of the law of conservation of energy. We also described that the decrease of static pressure results in higher velocities and conversely. Finally, we described how to estimate the pressure losses arising from friction. They depend from the length of the pipe itself and of all bends, branches and appendages in the piping. Thank you very much for your attention.